Hello everyone, welcome back. In this video, we'll be taking a look at continuity and continuing the thoughts or studies from the previous video. So, this following useful theorem says that f of x is the following are always continuous. That is, f of x equals to c and f of x equals to x and f of x equals to modulus of x are always continuous. So f of x equals to c is f of x equals to 2 or f of x equals to 3, which are just straight lines, they're always continuous. So let's go ahead and prove one of these ones. The rest of the proofs are pretty similar to this, to the one. So which one am I going to? Okay, let me go ahead and prove f of x equals to x. So remember the definition of continuity said that for all epsilon greater than 0, there exists a delta greater than 0 such that x minus c is less than delta, then f of x minus f of c is less than epsilon. So we have to show this definition. So let epsilon be greater than 0. We seek delta greater than 0 such that x minus c is less than delta. Then f of x remember here is x, and f of c, that means we substitute c in f of x, and when we substitute c in f of x we get c, so x minus c is less than epsilon. So we're going to say, so if you see this, it's just simple. We say choose delta equals to epsilon, and we know that x minus c is less than delta, which is equal to epsilon. So we get x minus c modulus of x minus c is less than epsilon. That's what we needed to show, and we're done with the proof. So the proof of the rest of the two are also pretty easy, so I'm not going to do that. So let's take a look at the algebraic limit theorem for continuity. So this is a pretty useful theorem, and it builds upon what we did at the start of the video. So it helps us, it says that if f of x and g of x are continuous at the point x equals to c, then the following are also continuous at the point x equals to c. So f of x plus g of x is continuous, so is f of x over g of x, and f of x divided by g of x, and c or cf of x, where c is some constant in the real number line. So from this algebraic limit theorem, we get that all polynomials are continuous. For example, the polynomial x cubed plus 2x squared plus x plus 1 is always continuous because x cubed is just x dot x dot x plus 2 dot x dot x plus 1, and we just said previously that f of x equals to x is always continuous, and the algebraic limit theorem says that when we multiply two continuous functions, we will of course get a continuous function. So x cubed is continuous, and when we add, and we also get that 2x squared is continuous because we also said that f of x equals to c is so for example f of x equals to 2 is we said f of x equals to c is continuous, so 2 is always continuous, so 2x squared is continuous, so is x, and so is 1. And the algebraic limit theorem states that when we add continuous functions together, the continuity is preserved. So all we get that all polynomials such as these are always continuous, and so are any rational functions such as x cubed plus 1 over 2x, as long as the denominator is never equal to 0. So we have a pretty useful theorem right there. So let's now look at another one, so, which is continuity of composites. So the algebraic limit theorem did not guarantee a continuity of functions like 3x squared plus 2. Although we know that this is continuous, we haven't proved it yet. We don't get this from the algebraic limit theorem. So this is a composite function, a root of a function. So so this theorem states that if f of x is continuous at a point x equals to n, and g of y is continuous at a point y equals to f of a, then g of f of x, which is also represented as g small circle f, so g of f of x is also continuous at the point x equals to a. So the proof of this is pretty simple. I'm gonna again use the sequential criterion for limits. So choose any sequence xn which tends to C, or in our case right now it's not C, which tends to A. And since f is continuous, we know that f is continuous. We're told that if f of x is continuous, so since f is continuous, we get that f of xn tends to f of C. And since g is continuous, since right here we have to say, I forgot to add this, since f is continuous at A, f of xn tends to, okay, not C right here, I'm forgetting it, sorry about that, f of xn tends to f of A. And since g is continuous at f, we have g of f of xn also tending to g of f of A. And that's what we needed to show, and we're done with the proof. So as you guys can see, it's pretty easy now to prove theorems in the world of functions, because we can just use the pretty nice sequential criterion which bridges the two worlds of sequences and functions. So we can always go back to the sequential world, prove theorems there, and come back. So let's go ahead and prove that f of x equals to ax plus b. Remember, ax plus b is any linear function, is continuous everywhere, and we know this is true because ax plus b, for example 3x plus 1, is just a line sort of like this. We know that it's always continuous. So let's just go ahead and prove it. So just like as we did at the start of the video, we have to show the definition. So let epsilon be greater than 0. We seek, so we have to show it's continuous at everywhere. Remember, in the previous video we were showing continuity at particular points. Here we have to show that it's continuous at the whole line. So we seek delta greater than 0 such that x minus c is less than delta. So here I use c because it should be continuous at the whole line, and c is at any point in the interval. For example, this could be C, this could be C, this could be C. So C is any point in the number line, the real number line, such that f of x minus f of c is less than epsilon. So here we're proving any linear function ax plus b is continuous. So this is the same. So f of x minus f of c is the same as ax plus b, which is f of x, and you substitute c into f of x, you get minus ac plus b, minus b is less than epsilon. So we have to show that. So ax plus b minus ac minus b simplifies to ax minus ac, and this further simplifies to modulus of a x minus c. So we have to show that this is less than epsilon. So now let's choose delta equals to epsilon over modulus a, and we'll be done with the proof. We know that x minus c is less than delta, so a x minus c will be less than a, and we know delta is epsilon over a. That's because that's what we chose it to be. We get epsilon over modulus of a. So these two cancel out. We get it's equal to epsilon, and we have just shown that a modulus of a x minus c is less than epsilon, which is the same as ax minus ac being less than epsilon. That's what we wanted to show, because right here, and we're done with the proof. So now we have just proved that all linear functions are continuous everywhere. So hope you guys have enjoyed this video. See you next time.